why we have our own special language. The symbol for the true population proportion is what?
Oh, this is P.
Yes. And the other two are what?
So I don't know what the first one is, but the second one is P hat, which is the sample.
Yes. So P hat sample, and I just want to say piña for that top one, just because that's the ñ sound, in Spanish.
Yeah.
So seeing it on a P, it makes me think piña. But anyway, that's nothing. That's just a red herring. So.
Okay.
But yeah, you're totally right. So P is for the population, P hat is for our sample.
Sweet. Okay, and then this, we just enter in the... Oh, wait. Okay.
We gotta check, make sure that sample size is big enough for the probability that we're looking at. So how do we figure if our sample size is big enough?
So we do the two equations. So we do n times p, and then we do n parentheses 1 minus p.
Close.
It has to be, n parentheses 1 minus p, n parentheses?
Try again.
Is it... is it P? Parentheses 1 minus P?
So...
Oh, wait, where's my... I thought those were...
And now I'm kind of like questioning myself. So let me double check, make sure that I'm not the one who's confused here. Because that's how nuanced this question is. So that just reminds me, I better jot down a note about this so that if it pops up on the test, I know exactly what I'm looking for.
Yeah.
Okay, so sample size. Actually, oh no, you're totally right. My bad. I'm sorry.
You're good.
For some reason, I thought it was P hat times 1 minus P hat. But actually, it is P.
Okay.
I don't know why I thought it was P hat. I'm going to have to just go over the equations and memorize that. But no, you're completely right then.
Cool.
So doing that with the problem, 0.25 times 100 is going to be 25. And then 1 minus 0.25 is 0.75 times 100 is 75. So both are greater than 10.
Yes. So true.
Yes. And that's, yeah. And actually, either one would have been correct because 0.1 times 100 is going to be 10 and 0.9 times 100 is 90. So either way, it would have been correct. So I'm glad that we double checked and made sure that it's correct because P is correct and not P hat is correct.
Yeah.
Because I'd hate to get that right for the wrong reason. Because then you just confuse yourself for a long time until you get corrected.
Yeah. Okay, and the requirements for conducting a hypothesis test are satisfied. Are we just looking at like sample size or what?
From what I'm remembering, that is the only thing that we care about. Because we're dealing with probability, we don't have to worry about normal distribution. Fact is, if you're flipping a coin, you know it's a 50-50 shot. If you're rolling a dice, it's a 1 in 6, you know?
Yeah.
So that normal distribution is already built in. So we don't have to worry, is this normally distributed? All we care about is our sample size large enough to offset how small a probability may be, you know?
Yeah.
So yeah, that's the only thing that we care about when it comes to probability testing, is that p times n is greater than, equal or greater than 10, and 1 minus p times 10 n is greater than or equal to 10.
Okay, so true then, right?
Yes.
Okay. Easy peasy. Okay. So is it 0.75?
Yeah, that's what I got. Just 45 divided by 60. %95 confidence interval. Okay. So we're looking at,
You just use Excel, right?
yeah, p hat.
Okay, so I got 0.64 and 0.86.
I do there.
Oh, wait. Oh, I'm not looking at the right thing.
Okay, that's what I did wrong. Change that. Okay. So 95% confidence interval. What is the margin of error?
I'm sorry, give me 1 second. Hmm. Okay, oh, that didn't even work. What? Okay, let me try this one more time. Okay, actually, my calculator's gave me an error. So, as the formula is the z, I forgot what we called that with the little snowflake.
Just the z-score.
Okay, so which is obviously 1.96, and then the square root p parentheses 1 minus p and parentheses over n. That's correct, right?
Yeah, that's our sigma is just going to be p times So the probability times the probability of it not happening divided by n, square root of all of that. That's our sigma now. So yeah, sigma times z, and that's our margin of error.
And are you using 45 as P?
Let's see. I'm using, where are you getting 45?
From...
Oh, I see where you made the mistake.
Oh, help me.
So we're looking at p hat, p hat times 1 minus p hat. What's p hat again?
The sample.
Sample what?
Sample proportion.
Yeah, so it's a sample proportion.
Mm-hmm.
So if we're looking at percentages, proportions, probabilities, what's one thing that we know about probabilities? What's the range that they fall in?
Oh, I have to make it into a decimal.
Exactly.
Okay. So I always do that with these kind of problems then.
Yeah, you have to figure out what p hat is, and you know that p hat is going to be a probability, so it's going to be between 0 and 1.
Mm-hmm.
So how do we find p hat here?
You do... Oh, so it's... Oh, 0.45 or 75. Oh, we did...
Yes.
Oh, okay.
Yeah. So just the probability, so the guilty over the total. So 45 divided by 60, 0.75.
Okay.
And if you plug that in, then yeah, you should get all the right answers. I think if you're doing it calculator or whether you're doing it Excel, you might have some rounding errors. I had to put questions 7 and 9 to the 4th decimal point just because it required rounding a 9, and I hate rounding a 9 to 0 and then rounding the next number up, you know?
Yeah. So
But
for
yeah,
n, it's obviously going to be 60. But do I do 60 or do I put 0.6?
so n, what's n?
What's n?
Yes.
It's the sample size.
Okay. And in this case, our sample size is measured in what's the unit that we're measuring our sample size?
Murders?
People on trial, but yeah. So our unit of measure is people.
Yeah.
And there's obviously no way that you're going to have 0.6 of a person. So we're looking at whole numbers here.
Okay. One of these days I'll get this right. Um, 0.0036.
Check.
I have to do that again, actually.
The margin of error. No, I got something different from the margin of error. Let me double check my calculation. So margin of error is z, which is 1.96 times sigma. What do you get for sigma?
Wait, did you get 0.007?
For which?
For margin of error?
No.
Oh, dang it. Okay, I don't know what I'm doing wrong. So sigma...
Yeah, what did you get for sigma first?
Nothing.
What? Why don't you have a sigma?
So I'm looking at the formula they gave us in the reading for margin of error. And we don't really need a sigma.
Well, yes and no. We don't need to be given a sigma because p hat times 1 minus p hat over n square root that is our sigma.
Oh.
So they just wrote out the equation instead of
okay, so
yeah, instead of just saying m is equal to z squared times sigma, they just expanded out the equation.
right. Okay, so for my sigma, I got 0.0036. Yeah.
Okay, I got a different sigma. I got 0.055901.
Okay. So this is what I put in. So I put square root 0.75 times 1 minus 0.75 over 60.
Let me think.
So weird.
So, okay, say that again.
So for my sigma, I did square root 0.75 times 1 minus 0.75 divided by 60.
Okay, that's the problem.
Okay.
That was just an order of operations problem. When you put it in that way, again, why I like Excel. When you put it in that way, it's square rooted 0.75, then times that by 0.5, and then divided by 60. Whereas you wanted to do the multiplication and the division, and then square root the entire thing.
Oh.
Yeah, orders of operation is just easier when you can put in parentheses and stuff on Excel.
Yeah. Man, I just need to do it in Excel. Okay, so let's see. So for my sigma, I got 0.0559.
Perfect. Yeah, that's what I got.
Ay.
And then margin of error is just sigma times z, so just that times 1.96.
So 0.1095. Rounding 0.11.
Yeah, see, I don't know whether I want to do 0.110 because I ended up putting down 1.096 because I got 0.10956. So if we round to 3, then the 9 becomes 0 and it becomes 0.11. It probably doesn't matter either way, but I don't know. What do you want to put down?
Wait, what did you get for yours?
Mine, I got 0.10956.
Oh, okay.
So if we were rounding 5, 9 would round up to 0, and then it'd become 0.110.
Yeah.
That feels weird to me. So I want to put in 0.1096, but it does say round to 3.
Yeah.
Let's just go 1.010.
Okay.
We got 2 shots on this, so that'll be easy to go back and change.
Let's see, the lower bound. So we can just use the Excel sheet for this. So for the lower bound, I got 0.64.
That's what I got.
And for the upper bound, I got 0.86.
And that's what I got, yeah.
Man, I love Excel. Okay, if you increase sample size. Decrease?
And why do you say that?
So when you increase the sample size, your standard deviation will get smaller and your confidence interval will also get smaller?
Yeah, perfect. So yeah, as your sample size increases, exactly what you said, your standard deviation decreases, which means your margin of error decreases, and the confidence interval is just the margin of error plus or minus our mean. So yeah, you said it more concisely than me, so that's you said it better. But yeah, no, you're perfect. Cool. Okay, question 11. Hypothesis test. Suppose the probability of something occurring is 1/2 or 0.5. What is the smallest n can be?
Ooh, how did we do this one last time?
So remember, NP has to be greater than or equal to 10.
Yes. Oh, so
luckily, 0.5 is the same as 1 minus 0.5, so you just have to do it once.
So is it 0.5?
What's the probability is? What's the equation?
The equation is n times p. Okay.
Yeah. So if we wanted to solve for n, we would then divide both sides by p. So we would get 10 divided by p.
Oh, 20.
Yeah, perfect.
Oh, I need to write that down. Okay, so when we want to solve for n, okay, cool. Okay, so 12. Oh, same thing.
Yes.
So 10 divided by 0.1. 100?
Divided by point. Yeah. And then something that these two show. So the further the probability of something occurring, the further it gets from 50-50, the higher your n needs to be. So the absolute smallest n you could have is the probability is 50-50, because then it's just 10 divided by 0.5, and that's going to be 20. But the further away you get from a 50-50 shot, then one of the ends is going to be small. So in this case, if we were to go p divided by 9/10, that's going to be what, like 11? But we know that that one's too small, and so we'd have to go with 10 divided by 0.1, which is 100.
Okay.
So as you get further away from the 50-50, one of the ends gets big and one of the ends gets smaller, but we always have to go with the bigger n. So the rule of thumb here is the absolute smallest n you can have is 20, and the further you go away from the 50-50, you're just going to have to get a larger and larger sample size.
Gotcha.
So if you ever get an n that's below 20, you know you did something wrong. So that's a rule of thumb you can use.
I'll write that down. Cool. All right, 13.
Okay, so null hypothesis, probability is equal to 0.6. Alternate is less than, so we're looking at one-tailed. Okay. N equals 80. What are we looking at? We are looking at 0.6. Oops.
So I got true. Oh, this is looking for the hypothesis, so yeah, this will be true.
Okay. Yeah, I got they needed at least 25 people and they've got 80. So I got true. Is that what you got?
I got um oh wait. No, I did not get 25. So I was doing the two indicators, so the n times p, I was doing that one for, but that has nothing to do with that question.
No, that's actually you're right. That's you want to use that equation.
Oh,
That's the only criteria we have for this. Like I said earlier, we don't care about normal distributions because we're working with probabilities. So the only thing we care about is our sample size large enough? And the NP greater than or equal to 10 is the equation.
Oh, okay. Okay, cool.
So what was the number that you got from it though?
So
Were you just having trouble, just math hiccup?
80 times 0.6, right?
No. It is
38 divided by 80?
Okay. Oh, no, I can totally see where that got you confused a little bit. And actually, the way you did it, I think, is another correct way to do it. Let me double check real quick. There's something that's telling me that the way you did it is correct, but I don't know how to prove it. So, but what we want to do is ignore n equals 80 for right now.
Okay.
What we want to do is figure out how many do they need for the conditions to be satisfied.
So solve for n.
Yeah, so we want to divide 10 by 0.6 and divide 10 by 0.4 and choose the larger of the two numbers.
Okay, 25.
Yeah, and they have n equals 80, which is much greater than 25, so we know that they're good to go.
Okay, that makes sense.
Okay.
Okay, and then p hat is going to be 0.475.
I got
Test statistic. Um, isn't P the test statistic?
we have so far we've gone over, I can think of 4 different test statistics that we've gotten over. So
Because P hat is the point estimator indicator or something.
yes. So if we're to look at, let's see, it's actually listed on this sheet here. And ignore what I have highlighted because it doesn't apply to this question. This just applies to the study that we're going to be doing. But here's all the different studies that we've done, that we've looked at so far, and there have been a few different statistics. So let me screen share with you real quick. So here's everything we've gone over. Quantitative, one sample sigma known, unknown, two samples paired. This is what we're going to be doing for our test because we're going to have the same person flip a coin and then have them flip again, but this time focusing on a desired outcome. Then we have two samples independent, and then we have ANOVA, and then categorical. We haven't gone over it yet this semester. But what we're doing right now, which of these does this experiment fall under?
Oh, let's see. So we're doing. No, I didn't actually read the whole thing. For the water quality study, about 6% of the. Two samples in one area. So it would be a, let's see.
Oh, just a second. I want to make sure I'm reading the same thing. Okay. So
So it would be.
So first off, 3 or more samples. Are we doing an ANOVA?
No.
Okay. So that one's gone, which means that our tests are, how'd they phrase that? Test statistic. So the test statistic, do you remember what we call the test statistic when we're using ANOVA?
I should know this.
It's the F score.
Okay, yes.
Yeah, there's one of the homeworks has you fill out an entire table doing all of it and stuff, so you can use that and just kind of save that in your homework file for study purposes. And so 2 samples independent. Is that what we're doing? How many samples do we have?
We're taking. It looks like. It looks like 2. They're testing it twice, but 1 sample.
So it looks like. So we have 1 sample. N equals 80. And okay, so that narrows it down. So that gets rid of everything down here. So we're just dealing with 1 sample. And actually, did you say the conductive hypothesis? Yeah, so we just have 1 sample, just the 1 N.
Yeah.
So if it were one of these two, what would our test statistic be?
Let's see. The t-score, right?
Yes, yeah, so t-score. And so we're down to 1 sample. Do we know the sigma?
No.
Do we?
No.
What's special about probabilities?
We get an alpha.
We have to have an alpha for everything. Otherwise, we can't tell whether something is statistically significant or not. So when we're dealing with probabilities, what's something that's unique about that? Find it in lesson 16. Maybe in this one. It's in here, but not directly. So let's go to lesson 16.
Okay.
So when we're dealing with statistics, I can find it here. Standard deviation is equal to right here. So we basically always have a sigma whenever we're dealing with probability.
Okay.
That means we're doing quantitative, 1 sample, sigma known. What test statistic do we use if we have sigma known?
Man, this is like forever ago. Okay, the P score. Wait, what was before T score?
That's what you got to remember. It's the first one that we went over.
Ooh, okay, wait.
So we had F score and then T score, and we've been working with the T score for just about for most of the time, for like a month and a half. But before we had to estimate the standard deviation, so sigma wasn't given to us.
Mhm.
Sigma was given to us, and so we had a very special type of test statistic. And basically, if you remember, here's a hint: the only difference is when we're using the probability applet. All of these, so when we are dealing with the t-score, we need to specify our yes, yeah.
Oh man.
And the only difference between the t-score and the z-score is that the t-score, we need to specify our degrees of freedom.
Yes.
But when we're dealing with z-scores, we're dealing with normal distribution, so we're totally good.
Yes. Okay.
So long-winded, but there's your review.
Okay.
Okay, so going back to the question then. Oops. So it's asking find the test statistic. So what are we calculating in this problem?
We're calculating for our z-score.
Yes, and you remember the equation for that?
Yes, they gave us the formula. So it's did they give us the formula? So is it gonna be like z equals, they said it was 95%, so would it be 1.96?
It totally would be if we're doing a confidence interval. During this case, we're not looking at confidence intervals. We are looking at we're trying to disprove a null hypothesis, but with a single sample. So our single sample, if it's far enough away from the null hypothesis of p equal 0.6, then we can say, oh, we can reject the null hypothesis. So if we were testing this hypothesis via a confidence interval, yes, z would be 1.96. Since we're not using a confidence interval, we need to calculate z.
Okay, so z is x bar minus u over sigma divided by square root of n. But we don't have, we're not given mu x bar.
When we're dealing with probability, what are the mu and x bar equivalents?
So we can use standard deviation instead of sigma, and we can use t-score instead of z-score.
So we've gone over a few different things, like for example, we have mu and x bar, and that's kind of the most basic thing. When we're dealing with
it's p hat minus p over square root of or standard deviation.
There you go.
Well, there's so many. I can't keep track anymore. Okay, so Mm-hmm. Huh. I'm not sure if I'm doing that right. Okay, negative 0.263. I'm pretty sure I did that wrong. I think I put my numbers in wrong.
Yeah, what are the numbers that you used?
So p hat is 0.475 minus 0.6. And then I got, so that was negative 0.125. And then I divided it by our standard deviation,
What'd you get for the standard deviation?
Well, isn't it the same as, maybe that's what I didn't do. Isn't p hat the same?
P hat the same as what?
Wow, no, that was so, what was I thinking? Hold the phone. 1 second. Oh, goodness. Can't seem to keep my numbers straight. 0.6. Negative 2.282.
Yep, that's what I got.
Oh, there's no way that's right. I have to do that all over again. That's funny. Okay, 282. Okay. So what is the p-value for this test? So we can just put this into the did you get 1 for your p-value?
I got 0.0112. And actually, I should have rounded that to 3, so 0.011.
Okay, so what is your decision? P-value is smaller, so you will reject the null.
Okay. So are you on question 17 or 18?
So 17 was reject the null.
Yes.
And then 18 is
This is a
There is,
very strangely worded question. And if
yeah,
it's what if it's what I think, if Sister Cook is doing what I think she's doing, this is
tricking
a
us.
very good trick question because I had to read over I had to scroll up and read over the question a few times before I think I know what she's doing. But what's your first impression? What do you think the answer is?
So what I want to pick is there is sufficient evidence to conclude that water quality in the area has decreased, but I'm pretty sure it's there is insufficient evidence to conclude that the water quality in the area has it's totally like a play of words.
Yeah.
So the null was it was equal to the alternate was that it was less than. So if there's insufficient evidence. I hate these. Okay, there's insufficient evidence to conclude that the water quality in the area has not decreased.
Okay. That's what sounds right. I'm just the way that they did the study is very weird.
Yeah.
Because for water quality, so water quality study, they're indirectly studying the quality of the water by measuring the health of the invertebrates. So normally 60% of the invertebrates have been healthy. So if the quality of the water has increased, then there should be more healthy invertebrates. If the quality of the water has decreased, then there should be less healthy invertebrates. But the way that they phrase this, so the researchers suspect the water quality in the area has decreased. They conducted a hypothesis test with a significance of alpha is 0.05 with the following hypothesis. Null hypothesis, p is equal to 0.6. Alternate hypothesis, p is less than 0.6. Turning that into English, the alternate hypothesis is the portion of healthy animals is lower than 60%, ergo water quality has dropped. So that's what the alternate hypothesis is saying.
Okay.
Our results are we have got, so historically there's been 60% healthy. We got 47.5% of them are healthy, so it's lower. We found that this is significant because our z-score and our p-value are low enough. So we reject the null hypothesis. So there is sufficient evidence to conclude the water quality in the area has decreased. So the last one.
Okay.
Okay, that just took a lot of interpretation.
Yeah, it was like
Because the way,
too much brain power.
yeah, no, the way it was worded, what I was thinking because this was a one-tailed test instead of a two-tailed test, I was thinking that she purposefully gave us the wrong tail so that we'd get a significant number, but it's in the wrong direction, so we can't say anything about it, you know? Like let's say just for example, let's say that they're testing to see p is less than 0.6, but let's say we got a p that was like 0.98 and it was significant, and it was so water quality has improved and it was statistically significant. But the thing is, that's not what they were testing because they're just doing one-tailed. They were testing to see if the water quality had lowered. So if that was the case, we would have to say the strangely phrased, there is insufficient evidence to conclude the water quality has not decreased. That's what I
Yes.
thought she was doing. I had to read through the question a few times to figure that out because that was just a tricky worded question.
Yes, I completely agree. Okay,
Okay.
I'll submit this time. The computer's being slow. Okay, which one did we got one wrong? Oh,
Oh, I actually got 100%. Which one did you miss?
wow, what did I put for? Oh, 16? What did I put for 16? I put down 0.001.
Oh, I got 0.01.
Oh,
So it looks like you just threw in an extra
yeah,
zero there.
well,
But was that the only one you missed?
yeah.
Okay. Then yeah, the rest of it looks good. Basically, this is what we've been doing this entire semester. The only difference is a few things you want to drill in your head.
Mhm.
Probabilities, we can always calculate the sigma. So we're
Mhm.
dealing with z-scores, not t-scores.
Write this down actually.
Okay. So yeah, you can think of, like we've done so far, mu and x bar, difference in zero when we're doing, a paired test. We want to make sure that the difference is equal to zero, difference is not equal to zero. So far we've had x bar, difference, and p hat. I'm trying to think. I feel like there's a fourth one too. I'd have to look back on that. But just remember that p is equivalent to mu, p hat is equivalent to x bar. We can always calculate the sigma, so we don't need to be given the sigma. But even though we're not given the sigma, we're still using a z-score, which means that we don't use the t probability applet, which requires degrees of freedom, which would give you just a little bit different answer, which may be enough to give you a wrong answer. So just remember, for probability, we're not given a sigma because we can calculate it. And because we can calculate it, we then use the z-score, which is the first applet where we don't need to give the degrees of freedom.
Okay.
And then also remember standard deviation, the equation. Yeah, the sigma equation is pretty different from the past ones. So I'm honestly not planning on memorizing it. I'm just going to write it down and have that be on my sheet of paper,
Yeah, no, for sure.
But just keep in mind that we can calculate sigma, but it is a different equation than what we're used to. And because like margin of error, and not margin of error, but like the upper and lower bounds, that stays the same. That's just margin of error. That's just p hat plus or minus the margin of error. So that stays the same. Sigma is one of the things that does change, though.
Okay.
So just make sure to write down those equations. But honestly, aside from those things, yeah, this is the stuff that we've been doing. So, that's the last one. Okay. So first thing, we won't be given sigma because we can always calculate sigma, which means we're using z-scores, not t-scores.
Okay.
Second, probabilities, the sigma, the way to calculate sigma, the equation's a little bit different. And then the other thing that makes this different from the other ones that we've been doing is the conditions we need. The conditions that we've been looking at so far, we either want normal distribution, or we want an n greater than 30 to compensate for a skewed. Here, and then the other one is simple random samples. Those are usually, for the most part, the other ones. Those are the two things that we're looking for: is normal distribution, either by the parent population being a normal distribution or n being greater than 30. And then the second condition is a simple random sample. We want to make sure that our samples are random and not just convenient samples or biased samples or anything like that. So those are the two conditions for pretty much everything else. This one is different. Our conditions are all numbers based, and those are NP has to be equal or greater than 10, and N times 1 minus P has to be greater than or equal to 10. So those are the main three differences between this section and everything that we've gone over in the past. Is sigma's a little bit different. So sigma's a little bit different. We're back to z-score, so we're not doing the t-score here. and our conditions on whether it's appropriate to take the test is different too, because we've only got one and it's numbers based as opposed to worrying about random sampling.
Yeah. Okay.
Okay. And then I'll screen share again and I'll show you what I've been writing. I'm going to tweak it some more before I submit it, but this is what I was thinking. So screen share. So I'll email you.
Stop this broadcast, but it'll still be us talking. Just